Okay, so now we have a look at some more logs and one more formula and a few examples of problems you might need to solve. But yeah, firstly, one final formula. This is called the change of base formula, and what it is a way of well, basically changing the base of a log. Okay, if the one you have isn't desirable, well, this is a way of changing it. So I'm not going to go into the derivation right now, but if you have log base a of x, you can change it to log base b of x over log base b of a. Okay, now what is b? B is literally any number that you want. It's usually either a base you already have elsewhere in your equation or expression, or maybe a base that works very well with a or x, that would give you an integer value once you evaluate one of those logs. So what is this? How does this look in practice? Well, this is one of the most common examples. Okay, something like this: log base 9 of 27. Now, it looks like 9 and 27 have some kind of relationship, but there's no integer power of 9 that equals 27. Okay, but what we can do is we can notice that they are both powers of 3, and therefore we can use the change of base formula and pick 3 as probably quite a sensible base to use, probably the only one that's going to work well here. And now we can just evaluate both logs. Log base 3 of 27, 3. Log base 3 of 9, 2. Okay, and we found that this simply equals 3 over 2, 1.5. Okay, or in other words, what have we just found? 9 to the power of 1.5 equals 27, which, well, seems quite simple, but probably something that not many students could tell you before you actually go through that whole process. Decimal exponents are not the easiest to do sort of by sight. Okay, but now to some other examples of various log rules that we can use, and a few little tricks as well. Okay, so not too hard to start off with. Log base 2 is 0.125. Now, the first step here, I think, would probably have to be changing the decimal to a fraction. That's going to make it a lot easier. And firstly, you might actually get to the answer straight away now, okay, because you might know that 2 to the power of minus 3 would equal 1/8. Okay, so we could just say that it's minus 3 right now, but maybe you wouldn't spot that, and okay, there is a better way of showing it. Okay, you could say that 8 is 2 cubed, okay, and 1 over 2 cubed is the same as 2 to the power of minus 3. Okay, and then we can use one of our log rules, okay, to take this power and put it at the front, if you will. 3 times log base 2 of 2, and log base 2 of 2 is just 1. Okay, so it's minus 3 times 1, minus 3. Okay, okay, not too dissimilar in this question. The main thing here would be, I would say, recognizing that the square root is the same as doing the power of 1/2. So, okay, because we can't do the square root of 27 in our heads. Okay, then again, using that third log rule and moving that power to the front, and then suddenly we have a log that we can do. Log base 3 of 27 is just 3. So 3 over 2, or 1.5. Okay, getting a bit trickier now. Okay, now we're solving a log equation. Okay, not solving an equation with using logs. So we have an addition of logs, and they have got the same base, so we can use that first log rule, that addition rule, and multiply x by x minus 2. Now, we can't evaluate this log or anything like that. What we can do, okay, if you ever get slightly stuck in a question like this, you should always consider moving from log form to exponential form, or vice versa. It might turn out that that will be useful. Okay, and in this case, I think it is. Okay, if you just refer back to the basic definition formula for logs, you could convert it as so. And all you have now is actually just a quadratic equation. And you should be able to solve these by now in IB, ideally. Maybe by factoring, for example, x minus 4x plus 2. So, well, you might say that x equals 4 and minus 2, but you actually can't do, well, you should always check in any equation, really, whether your answer makes sense. So, log base 2 of 4, yes, that would work. And log base 2 of 4 minus 2, so 2, that would be valid as well. Okay, so 4 seems to be a perfectly good answer, but minus 2, okay, log base 2 of minus 2, well, what power of 2 would give you minus 2? Well, nothing. That does not work. Okay, you can't do log of a negative. Okay, with a positive base. So just 4, not minus 2. Okay, question 4 here. It's actually, well, in some ways very simple, but in some ways one of the hardest questions to explain that I've come across. And this is actually part of an IB question from the past. Now, I'm going to start off by saying log base 2 of 125. Well, log base 2 of 128 would be 7. So I'm going to just say for now that this is 6.9 something. It doesn't actually matter what it is, but let's say it's 6.9 something. And what does this mean? This means that 2 to the power of this decimal equals 125. Okay, and then, well, we can use that result to go back to our original, the thing we were given originally, and say that 2 to the power of this log is the same as 2 to the power of this decimal, 6.9 something. But what do we just write down here? 2 to the power of 6.9 something does equal 125 itself. Okay, so this is kind of a strange result, but we are finished here. It does equal 125. It kind of sounded like we were going around in circles there, but this actually gives rise to this formula here, which I think used to be in the old HL formula booklet maybe, and it is not now, I believe. But any constant to the power of log base of that constant of any other number, x, or in this case 125, will equal that number, x, or in our question 125. Okay, a formula that you may want to learn even. Okay, but as we've seen here, it can be sort of solved logically anyway. Now finally, I think this was in a similar question, was in an old HL exam maybe. Now, whenever we have log question where we have logs with different bases, that is your first clue that you're going to be using the change of base formula. Okay, you will always want to sort of go to that straight away if we see different bases in one question. Okay, so well, what was the formula again? This here. Okay, so remember to put essentially this number on top, this number on the bottom, and choose any base you want. Now, we're essentially starting with 2, and in this strange sequence ending with 8. Okay, so 2 and 8, I'm going to say base of 2 seems like it would be helpful for some reason. Okay, so that's what I could change the first one to, and I'm going to change every single term here into log base 2 form. Okay, and so on until the last log. Now, not many of these can be evaluated nicely, okay? Obviously, as we said, log base 2 of 8 is 3, log base 2 of 2 is 1, okay, maybe you could do 4 as well, but there's a better thing we can do here, which is we've got some cancellation, okay? This is just lots of fractions multiplied together, okay? So we could cancel out log base 2 of 3 and log base 2 of 3. We could cancel out log base 2 of 4, log base 2 of 4. Okay, and even though you stop seeing it, you would keep going, and log base 2 of 7 would be the numerator in this fraction, and then cancel out here as well, and you would be left with log base 2 of 8 over log base 2 of 2. Okay, 2 logs that you can evaluate easily to 3 and 1, i.e. 3. Okay, so even though you had what was probably some horrible decimal in every single one of these, they would multiply together, and you can show it through change of base formula and cancellation. They'd multiply together to get you 3 exactly.